In this video, we're going to start discussing different types of collisions, because not all types of collisions behave the same way. So the first type of collision we're going to discuss is called the inelastic collision. And this is when two objects collide. And remember, for right now, we're sticking for head-on collisions. We will move on to what we'll call glancing collisions at the end of this topic, where there's going to be X and Y motion. For now, we're worried about the X direction. So momentum is conserved in an inelastic collision, but kinetic energy is not. And it's not conserved because of what we learned in topic 5. So as the object is colliding with the other object, so if you imagine two bouncy balls and we could freeze frame them as they collided, they would squish into each other. So a force of object 1 on object 2 is applied over a distance, which means that there's work being done on the other object, which leads to a change in kinetic energy. So whenever there is a collision where the objects compress during the collision, there is a transfer of kinetic energy. Kinetic energy is not conserved. There is either a loss or a gain. It doesn't mean that energy is not conserved. That's an entirely different issue. This means that we can, for inelastic collisions, apply the conservation of momentum equation that we derived in the previous video. Once again, reminding you, I always write it down for two objects, but you just need to add an additional initial term and final term for each additional object that is part of the collision. Now, there is a special case of perfectly inelastic collisions, and a perfectly inelastic collision is when the objects stick together after the collision. Momentum is still conserved. Kinetic energy is not, for the same reason discussed earlier in this video. So there isn't a difference between inelastic and perfectly inelastic when it comes to kinetic energy conservation. However, because the objects stick together after the collision, that means that while they initially were two separate objects with two separate velocities, since they're moving as one object stuck together, their final velocity is going to be the same, which means you can factor that out. So it's very important to be able to identify a perfectly inelastic collision, because while you're still applying the conservation momentum equation, it may look like you have too many unknowns because final velocity 1 and final velocity 2 are the exact same value, and so you don't actually have two unknowns. Now, I typically write this in terms of the objects sticking together after the collision, but it is possible to have a perfectly inelastic collision where the objects are initially one object and they separate. So something like a person jumping off of a skateboard, where the person goes in one direction and the skateboard then flies backwards. So initially, they would have the same velocity, and then you're adding together the masses, because that's conservation of momentum. But afterwards, they would have two separate velocities and two separate momentums. So you can have what I call a perfectly inelastic collision inverse, where they start as one object, and then they separate after something happens.